All right, let's jump right in. We've got a massive piece of AI news today. We're looking at a really exciting ACL 2026 research paper that takes aim at one of the absolute most stubborn problems in AI development right now: large language model hallucinations, specifically when we're dealing with mixture of experts or MoE architectures.
So here's the $1 million question. Can we actually fix AI hallucinations without ever touching the model's weights? It sounds almost too good to be true, right? But researchers, Fang and colleagues, set out to answer exactly that in their new paper. And honestly, what they found is going to completely change how we think about putting these models into production.
Here's our roadmap for this explainer. We'll look at the hallucination problem, the MoE mystery, introduce EAACD, see how it calibrates predictions, and finally, go over a practical implementation guide. Part 1, the hallucination mitigation problem, and the real limits of our current methods. Right now, if you're trying to fix hallucinations, you're usually stuck between a rock and a hard place. You've got prompt engineering, which is super accessible but rarely fixes the model's underlying knowledge representation. Then you have model optimization, your fine-tuning, your RLHF. But here's the catch with those. The second your deployment environment shifts outside the training distribution, they predictably break down. They just don't generalize well across different domains. So to get around that, this really clever technique called contrastive decoding emerged as a middle ground. Basically, instead of messing with weights or tweaking prompts, it manipulates the actual token generation process. It looks at the differences between layers during the model's forward pass. And it's been awesome for standard transformers like GPT, because higher layers naturally systematically diverge when they're generating facts versus when they're hallucinating. But, and this is a huge headache for developers, if you try to use this exact same standard technique on cutting-edge mixture of experts models, it completely falls apart. The results are just wildly inconsistent, which begs the question, why? That brings us to part 2, the MoE architecture mystery, and why traditional contrastive decoding breaks down. Okay, so remember that MoE models route data through specialized experts for each token, while the authors of this ACL 2026 paper mapped out what happens in these layers, and it shatters our standard assumptions. They found that in MoEs, where experts are shared, the traditional contrast signal just vanishes. The probability distributions are just too aligned to draw a boundary between fact and fiction. But they did find something else. The higher layers actually show very distinct expert activation patterns. This is where it gets really cool. Those higher layers are basically encoding the truth through their routing choices. When the model is generating factual sequences, it routes cleanly through a stable, reliable set of experts. But when it's hallucinating, the routing goes totally haywire. It's erratic, constantly switching experts, kind of like someone nervously guessing answers on a multiple choice test because they didn't study. All right, part 3. Introducing EAACD, a decoding time intervention. Because of that crazy routing discovery, we can shift our whole strategy. We stop looking at layer probabilities and start looking at expert reliability. Enter EAACD, Expert-Aware Adaptive Contrast Decoding. It's an incredibly elegant way to exploit those stable versus erratic routing patterns we just talked about. And the absolute best part is it happens entirely at decoding time. You don't have to retrain your giant model to calibrate these predictions and suppress hallucinations. And just look at what they pulled off here. The researchers showed EAACD beating all the baselines across 4 different QA datasets. No architectural changes, no extra training steps. They are literally boosting factual accuracy purely during inference, which is just brilliant. Let's move to part 4, how EAACD calibrates predictions step by step through the deterministic sequence. This pipeline operates solely on those high-layer expert activations following a strict 3-part sequence. First, expert grouping by reliability. Second, contrastive calibration. And third, hallucination amplification via attention masking. Let's break down step 1. Instead of relying on rigid, static thresholds, which usually fail across different domains anyway, it dynamically scores the experts for every single query. It looks at confidence, meaning the actual probability magnitude, and consistency, so how stable it is across similar prompts. Based on that math, it splits those high-layer experts into a higher reliability group and several lower reliability groups. Then in step 2, we get to the contrastive calibration. It takes those lower reliability outputs and uses them as negative references. Literally, it subtracts their mathematical influence, their probability mass, right out of the base token distribution. So it's actively, mathematically punishing tokens that align with that confused, erratic expert routing. Finally, step 3, hallucination amplification. Now, that sounds counterintuitive, right? But to really draw a hard line between truth and hallucination, EACD applies targeted attention masking. This isolates those erratic routing paths and forces the decoder to treat them as explicit negative constraints. You are basically weaponizing the model's own hallucinations against itself to make sure the final output is factual.
And that brings us to part 5, the Developer Implementation Guide. How do you actually bring EACD into production?
If you're an engineer building with this, your first hurdle is that standard inference engines usually hide the expert selection from you. They just spit out token probabilities. So you're going to need a runtime that exposes those high-layer routing tensors. Think VLLM, TGI, or maybe a custom Triton setup. On top of that, you'll need to build out a dynamic reliability scoring system, like a sliding window metric per batch, to crunch those confidence scores on the fly.
Now, full transparency, because you're adding this math into the decoding loop, you should expect roughly a 10 to 20% increase in latency per token. But look, if you're deploying a QA system where being factually accurate is make or break, like in legal or medical AI, that is generally a highly worthwhile trade-off. Plus, batch generation can definitely help soak up some of that overhead. Just keep a few constraints in mind before you start tearing up your codebase. Right now, this is mostly verified for QA tasks, so performance on open-ended generation is still a bit of an unknown. It also assumes you have access to unquantized high-layer expert activations. If you aggressively quantize those paths, you might accidentally destroy the contrast signal you're looking for. And finally, there's no official reference implementation out there just yet, so you'll be writing the scoring logic yourself straight from the ACL proceedings.
So, as we watch this methodology leap from an ACL research paper to likely getting native framework support soon, it leaves us with a really big question. Is expert-level decoding the ultimate key to taming MoE hallucinations? Are we about to see inference time routing tweaks become the absolute gold standard for AI reliability? It is a fascinating paradigm shift away from traditional weight updates. Thanks for hanging out for this explainer. Go check out the original paper by Fang and the team for all the math, and keep building.